Thank you, everyone, for coming. I'm actually going to hand over to Ashley Llorens, who's our CVP Managing Director for MSR Accelerator, to provide the formal welcome to our Nuclear Fusion Summit.
Well, thank you, and I'll just give a very brief welcome to you all. And so really appreciate you being here. Welcome to our distinguished speakers. Thanks to all who are joining us from away. You know, the folks that come from the farthest are the sharpest experts in the room always, so really appreciate that. Thanks to the organizing committee for putting this on and for all the folks that are here attending. So I'm Ashley Llorens, part of the leadership team in Microsoft Research. I lead the global Accelerator team, and we accelerate research and innovation from ideas to impact. So we kind of help Microsoft Research explore potential frontiers in science and technology. And I'm especially thrilled that we're having this discussion today. And that's for two reasons that I think are important to all of us here, or perhaps they are. One is the idea of the promise of a more intelligent future. And we've seen very viscerally over the last few years the increasing correlation between our ability to spend energy in the form of compute and in doing so extend human intelligence through the advancement of computation and AI. And so I'm interested in seeing that trend continue. But of course, the other thing is the imperative of a sustainable future. And all these very ambitious goals that companies like Microsoft and governments around the world have set out are super important for us to meet. And so on the face, these can be competing objectives. And minimally, I'd love to see us be able to make Pareto improvements in this trade space. But maybe even more ambitious would be the ability to make this actually self-reinforcing, right? So through the application of compute and AI, actually be able to advance sustainability inherently. Microsoft Research is not that big as a fraction of Microsoft. We're order 1,000 folks. Microsoft is 250,000 folks. And so part of what we need to do very well in Microsoft Research is choose which problems to work on. And so, I'm excited that, we're here to kind of explore this frontier together. I'd invite all the Microsoft folks in the room to think about this in that context, Certainly this is a problem to understand more deeply. And where, if at all, should Microsoft Research really be invested in advancing these technologies? So with that, thanks once again to all for being here, and I'll turn it back over to Kenji and Ade and team.
Thank you so much, Ashley. And as he said, we're absolutely honored and delighted to have you here and to have our distinguished speakers who are international experts in nuclear fusion. And there's a huge recognition that the application of AI for science could really help accelerate bringing fusion to the grid. And it's so exciting because of the transformational potential of that for virtually unlimited, clean, and sustainable energy. And so this is perhaps the first time that we have brought together world experts in nuclear fusion, researchers and innovators from across Microsoft to have this discussion. And we hope this is just the start of a journey that we can have together. So I'm going to hand over to Shruti, who's going to run through the day.
Hello, everyone, and welcome to the first Nuclear Fusion Summit in Microsoft. We are running late on our schedule, but we'll start. We already have the opening remarks. We'll start with interesting and very inspiring keynote lectures from Steve Cowley, Richard Buttery, and David Humphreys. Then we'll have another lecture from Zulfi, our CVP for Quantum. And then we'll have a short break, depends on now how much time we have. Just one thing to note, we will take questions after the talk. So anything you have, please hold it in, then ask it after the talks. We're going straight to the research lightning talks, which all of our researchers have prepared on what can be what research they are doing and how can it be used for fusion, and then we'll head to a panel discussion. And I hope you get inspired, you learn a lot, and join us on this advancing nuclear fusion with AI journey. Thank you.
Thank you very much, Shruti. So our first speaker is Professor Sir Stephen Cowley. He's currently the director of the Princeton Plasma Physics Laboratory. He was formerly the chief executive of the UK Atomic Energy Authority and headed up the Cullinan Centre for Fusion Research. He was knighted in 2018 for services to science and to fusion research. We're absolutely honoured and delighted that Stephen is here to kick us off and really give us the insights into fusion to kick-start the day. Thank you, Stephen.
Thank you, Kenji. So I've been thinking about this for some time, whether we can use AI effectively in fusion to accelerate the delivery of fusion power. And so I'm going to try and explore that in this first time. I was also asked to kind of introduce fusion a little bit, which I will do. This isn't Fusion 101. We don't have time for that. And most of you are very technical, so you probably had something like that in the past, but I will prompt some of those things. We're starting to use AI. And I think that particularly at in General Atomics at the D3D facility, it's becoming part of the toolkit of controlling the plasma, analyzing the data, that kind of thing. But I'm interested, I think, in a much more challenging question. Could AI actually be the key ingredient in finding an optimum configuration for fusion power that really delivers electricity at a cost the consumer wants to pay for electricity? At the moment, we don't have an answer to that problem. Despite what you'll hear in the press, etc., and we're not trying to impress VCs right now. Fusion is not ready to be delivered in a short amount of time. There is a tremendous amount of development that needs to take place. The question is, can we shorten that timeline effectively by the use of high-performance computing and by AI, and by the use of the data that comes from the existing fusion experiments. This, for instance, is Professor Egerman Coleman's from his Nature paper. This is work that was done on the General Atomics D3D machine in order to heal what we call magnetic islands inside it, etc. But as I was thinking about this, and I always start my talks a bit like this, I always tell people that I give talks a bit like a James Bond movie. You always start with that bit of the James Bond movie before the credits roll past you, where he's on top of a train fighting the bad guy and they're about to go into a tunnel and you're not sure they're both not going to be decapitated. And so I usually do something like that. Let's see. At the beginning, so you never see an introductory slide from me until you're about 2/3 of the way through the talk. In November of 1945, all the incredible scientists at Los Alamos were thinking about going back to their universities. The Nagasaki bomb had been dropped in August. Victory had been declared, peace ruled, and Enrico Fermi and Robert Oppenheimer and Hans Bethe and people were all thinking, we're going to go back to our universities. And the question is, just like you're talking about today, what are going to be the great questions we're going to work on? What are the things that we haven't solved in the year and a half we've been in Los Alamos that we ought to be working on at that time? It's kind of interesting, and these were superstars, I mean, unbelievable people, right? But the conference was classified. It was so classified that no notes were allowed to be taken because all kinds of speculation, and I'm sure there's a lot of speculation about more advanced nuclear weapons and things like that happened at that conference. But the thing you should know is that Enrico Fermi got up and talked about doing fusion and control fusion. And he talked about magnetic confinement at that time. And when I was a student at Princeton in the early 1980s, yeah, I'm that old, people talked about the fact that there was Fermi's theorem that said you couldn't confine plasma in simple toroidal field alone. A toroidal field is a toroidal solenoid, basically just a field that bends around in a circle. And this was called Fermi's theorem. Nobody knew when Fermi proved this theorem and whatever. But this document I came across because a journalist pointed out to me is a declassified intelligence British report by Philip Moon, who was professor of nuclear engineering at Birmingham for many years, and part of the British contingent at Los Alamos during the war. And what was happening by November is that we knew that you Americans were going to ban us from knowing any more American nuclear secrets. And so the British government had instructed all the British scientists at Los Alamos to collect as much together possible to bring back because they were going to be leaving soon. And in 1946, the McMahon Act was passed, which banned Britain from having American nuclear secrets, and that continued until the Mutual Defense Act of 1958. So this was Philip Moon spying on the Americans. He was in the audience, and he took notes. And these are the only notes in that meeting because everybody else was banned from taking notes. And this turned up, because it was declassified eventually, in the Churchill College archives in Cambridge. And there is just a short section on Fermi discussing how to do thermonuclear fusion by confining a plasma in a magnetic field. So sorry, that's a bit of fun, and it's of no use to you whatsoever, that information. Let's start with this. Now, there's one fusion reaction that's a lot easier than all the rest, and that's the one between deuterium and tritium. Deuterium and tritium, if you bring them together, of course, they'll repel because they're positively charged. But when you get close enough that the strong force that binds the nucleus together can act, they will form, for a moment, helium-5. So here's deuterium, which is a proton and a neutron, and here's tritium, which is a proton and 2 neutrons. Put them together, ram them together, even though they repel, get them close enough, they'll form helium-5 in actually a J3 half state for the physicists in the audience. The reason this has an enormous cross-section for a fusion reaction is it's resonant. You form helium-5 in a J3 half state, but that's only metastable, and it splits up into helium plus a neutron. And this reaction has a cross-section that is 80 to 100 times larger than any other fusion reaction you can think of. And it also, because the charges are only singly charged particles, happens at a much lower temperature than all the other fusion reactions. It's one of God's jokes, of course, because this doesn't exist in nature, right? It has a half-life of 12.4 years and will decay over time. And so if you want to do this reaction, you've got to make tritium to do it. But fortunately, you can do that by bombarding lithium. You can bombard lithium with the neutron that you get out of here, and lithium-6, for instance, which is 7.25% of naturally occurring lithium, will split into helium plus a tritium. It also gives you some energy, and you can take that tritium and you can put it back in your reactor and make a reactor. So your fuel actually is lithium, and lithium-7 also has a reaction, and I'll get to that in a moment. Your fuels are lithium and deuterium. There's enough lithium in seawater basically to power the planet for 30 million years entirely by this reaction. It's 0.2 milligrams per liter of seawater. Now, separating lithium from seawater at this point, it's not worth doing because we've got lithium in much larger concentrations, but this gives you a scale of how much energy you actually have in fusion. But when you do this reaction, this is actually the hard reaction to do. This one will happen basically at room temperature because the neutron does not repel the nucleus of lithium, so this can happen basically at room temperature. In order to get this to happen, you have to heat the deuterium and tritium to roughly about 200 million degrees. And once they're at 200 million degrees, when they're flying around, they bump into each other. Occasionally, mostly they will just glance off each other, but occasionally they hit smack on and you'll get a fusion reaction. But you need to heat it to about 200 million degrees. And therefore, it has to be in the form of a plasma, an ionized gas, because it's so hot, the electrons will not stick to the atoms at that point. And you have to somehow control something that is at 200 million degrees and hold it and get that to happen. Now, for future use, all of the nuclear physics can be summed up basically in one nice formula. This is the power density in fusion if you heated deuterium to a temperature around 200 million degrees. This is the pressure in atmospheres of that plasma, and this is in megawatts per meter cubed. That's your fusion power density. Now, typically, the plasmas that we can find have a few atmospheres of pressure. So particularly, say, ITER, which is the International Tokamak 7, the pressure in the middle is 7 atmospheres. This is 49. You're at about 4 megawatts per cubic meter of your device. That's not bad, because typically your device will have about 1,000 cubic meters, so that will be 4 gigawatts of power you're getting out of your device. That's pretty good. This is multiplied by a number, by a function of the temperature of your plasma, but this is 1 at about 150 degrees, million degrees. 150 million degrees, sorry, not 150 degrees. That would be nice. The reason this is a difficult reaction is this is a radioactive gas, right? And you have to handle that radioactive gas, and you have to make sure everything's safe and you don't have releases of that, etc. But anybody who suggests that they're going to start fusion with any of the other fusion reactions either has a lot smarter than anybody yet in fusion, or hasn't done the calculation. Because this is so much easier than everything else. And you'll find that a lot of fusion companies, and we're seeing a lot of fusion companies right now, come out and they start by saying, oh, I want to do a nicer reaction, like deuterium-deuterium or deuterium-helium-3, right? With time, they all go back to deuterium-tritium because it's really a heck of a lot easier to do. Now, people say, well, how can you possibly get 200 million degrees? We've done that. Right? This is the record of a magnetically confined sort of super shots, as it were, the best results we've ever produced. So we've actually heated deuterium and tritium up in 2 devices in the world. Tokamak fusion test reactor at Princeton in 1994 got 10 million watts of fusion power for about a second out of a plasma that was at about 250 million degrees. And the reason it only went for a second is that the device is held in the plasma is held in a magnetic field, and that magnetic field is made by big copper magnets that get very, very hot if you run them for too long, right? This is what happened at the Joint European Torus at Culham. Here in 1997, 16 megawatts, but this wasn't actually, it's the one I used to boast about before the recent results, because it went up to 16 megawatts and it came down rather rapidly for rather not very good reasons at the end of that 16 megawatts. But last December of 2023, they took it up. And for the whole time they could sustain the discharge, they were above 10 million watts coming out of the device. It was at 230 million degrees in that case, I think, at that time, and we actually had seen that reaction. Now, one thing you should know about this reaction is that pretty much any device we'd make in fusion, the neutron goes right through the plasma and out into the walls. And that's fortunate, because in the walls somewhere you're going to have your lithium, so you make your tritium in the walls. We call that the blanket system, and we'll get to that in a moment. But, going the wrong way. None of these, but what you can get is that the helium that's produced is what's called an alpha particle, helium, which only has 1/5 of the energy from your fusion reaction comes out as energetic helium. That helium goes through your plasma, bumps into the deuterium and tritium and heats it. Right? And you can get a self-sustained fusion burn where it's actually ignited if you get enough fusion power to support the losses of heat so the thing heats itself. And so that helium is your self-heating. None of these shots were self-heated. Right? The amount of self-heating was negligible compared to what we were putting in at that time. Now, the National Ignition Facility, which did I'm not going to show these results because it's just too much to show, which about 2 years ago got actual ignition. They saw some heating, self-heating by things. It was an actual fusion ignition. But that was with a laser and in a configuration that probably doesn't really scale to commercial fusion. So this is fantastic. What do you now do if you want to say, yeah, we can do fusion? The question is, can we do fusion that will actually make some energy? The Europeans and the Chinese have taken basically this kind of configuration. This is, I'm going to get to the configuration in a moment, but this kind of configuration and taken it and said, what would an actual a prototype reactor look like? This is the European demo reactor, demonstration reactor. It's taken about 9 or so years of a team of about 60 people doing CAD drawings, etc., to build this, build a design of this. So you make it bigger, because what you want to do is to make the heat leakage out of the plasma less than the fusion supply, so that it heats itself. And this gets to 9 meters major radius. This is a humongous size machine. These are superconducting magnets, these yellow things, that in the plasma. This is not an attractive reactor design. Estimates are that it would cost $50 billion to build, right? And the point is, where we stand right now, if we just go in the linear path to fusion, we will come up with a fusion reactor, but not an attractive one, not one that somebody wants to actually play for commercial reality. The danger of that is a political one. As you've now demonstrated that fusion can happen, but it's too expensive to be of use, right? And that would be a big shame, because we don't know enough in order to, and we want really to evolve faster, cheaper, more efficient fusion systems that will actually get us to the market with something that actually can deliver electricity at a cost. So, I think the general concern about an energy system that's dominated by renewables is, of course, the intermittency of renewable energy. Solar and wind are coming down in price in a really spectacularly good and pleasing way. But there are times, and it turns out it's December in the UK, when the wind doesn't blow very much in December in the UK, and certainly the sun doesn't shine, right? And so you have parts of the year where you don't have any other source, you don't have sources of energy that can actually fill the gaps. These kind of sources people are calling firm energy sources. You probably all know this. And nuclear, of course, is a very good one for that, although it tends to be with fission, you want to leave it on 24/7, so you don't fill the gaps, you just fill. But with this in mind, under the previous administration, they launched something called the Bold Decadal Vision for Fusion. Right? This was a summit we had in the White House in March of 2022. In fact, people from the Office of Science and Technology Policy came to Princeton in January of 2022 to discuss, is it realistic to try and go for a decade to first electricity from fusion, right? And we sat down and talked about this. And then we had this, I'm just boasting that I was in the White House, actually. The person with the blue hair is not me, I'm the one next door. But this was what was happening at that time, right? And I think we were all hoping, and just before this report of the National Academy said, bringing fusion to the grid, said this statement here, which is the Department of Energy and the private sector should produce net electricity in a fusion plant in the United States in the 2035-2040 timeframe. So since that, we at Princeton have taken this as the challenge, right? We should make some electricity, actually make something that produces net electricity from the plant in that kind of time frame. That's not 3 years from now, and it looks like it's a long distance from now, but we've got an awful lot of technical problems to solve in the intervening time. The problem, of course, is if you want to do something like this, you need a budget. And what we didn't have was a bold decadal budget. We had a bold decadal vision, but not a bold decadal budget. And everybody says, well, we need a Manhattan Project in fusion and things like that. Well, the Manhattan Project had a certain amount of cash. We don't have that kind of cash at this point. I'm very optimistic about the Trump Department of Energy. The new Secretary of Energy is a very technical person, very interested in technology and science. And the team that's coming in underneath the new secretary, very interested in science. I think you'll find less emphasis on what they call industrial policy and much more emphasis on fundamental science there. And one of the things that we've been discussing is, could we speed up the development of fusion and make fusion a technology that's essentially the first technology that was really enabled by high-performance computing and artificial intelligence, right? Cut the corners on the development pathways by using these tools. Now, the reason I think that we're in a particularly good position for that is the real advance was not those shots, those fusion shots that I show you. The real advance of the last 10, 20 years in fusion science, and a lot of this went on at General Atomics, was the development of predictive models that are based on physics and based on science that allow you to actually calculate what goes on inside of a fusion machine. We can't actually we haven't got fusion reactors to train a bunch of AIs on, right? Because we don't have any fusion reactors, right? So if we're going to optimize and go forward, we're going to have to think, how is it we use the data that we have from machines now, and we use the computations which will allow us to compute the future state of things, right, to produce models that can optimize the position, as it were, in configuration space of engineering designs for the future, right? So I think that's the challenge, and the thing that I think this room full of people could really influence greatly, because I'm a little at sea as to exactly where we're starting to put AI into our models and things like that, but we're not just going to run a bunch of things and come up with an answer and say, that produces 5 gigawatts of power and was this big, etc. Because each time, so let's see. Okay, this is my introductory slide at this point. I think we don't quite, net electricity is the definition I would like to say for this. And talking to the Trump administration, they'd like to see it by 2035, the beginning of that period. Right? That's what a pilot plant is. It's not a commercial plant because first of a kind is never going to be commercial, right? And there are lots of questions that can only be answered when you've built one and you maintained it for a few years, and your utility says, yes, I'm going to spend whatever it is, $6 billion, $7 billion on building one of these things. They want to know that it's going to last more than three months, and they want to know how do you maintain it. They want to know these things. So this pilot plant, in some sense, is not really a prototype of a commercial plant, but it shouldn't be too far from it. So there's some kind of sociology in that. Can we build a plant with today's knowledge and today's materials? We can build an expensive one, but I'm not sure we can build one that wouldn't set us back and take too long to build. I think, I make the analogy, so when we talk to private companies that are in fusion, they say, well, we have a portfolio approach. And there are 40 different private fusion companies around the States. And frankly, at least 37 of them are slightly bonkers. And a portfolio approach to fusion might not be what we need to do is probably more like the Manhattan Project than it is you just have 40 shots on goal, right? Because we haven't actually done this before, right? This is not a technology, it's a technology readiness level of 7, right? And what we need to have is a bunch of companies figuring out how to do it cheaply. Right? This is a technology that we've never done before. And using calculations and AI, right, to actually find a sure route to something that will work, given that every time we make an experiment, it's going to be many $billion, is surely the way to move forward. it's sort of foolish to imagine that we'll do fusion by trial and error. This is not Thomas Edison, making 50 different light bulbs and saying this one works the best. We'll evolve that one and then 50 more, etc. Right, in a sort of genetic algorithm approach to innovation. We've been doing trial and error in fusion and inspired guesses for 70 years, right? We've got to use something now that gets us in the right direction. So, a bit more physics. I promised Chris there would be some formula. We'll start with some very simple ones. The standard magnetic configuration is just a bent solenoid. So this is a coil. Makes a field going around the long way in the torus, right? And you fill a vacuum vessel with a plasma of ions and electrons, positive charges, negative charges. And then what you do is you change the magnetic flux through the middle of that. And Faraday's law says you induce a voltage around the loop. And what happens is your electrons go in one direction, the ions go in the other direction, and you have a current, the red arrows, like that. And that current is throughout your plasma. And the current on one side attracts the current on the other side because like currents attract, right? And they pull itself together and it pulls itself off the wall. It combines a pressure that pushes outwards from the middle to the outside. And that attraction of the current with itself, which is called the pinch force, is what holds your whole magnetic configuration together, right? That's the principle of the tokamak. And what you have is you have a bunch of other coils here that can shape it and steer that plasma because, again, like currents attract. So if you have a coil with the current going in the same direction as the plasma, it'll pull the plasma that way. If you have a current with the opposite direction, it'll push it away. So you have control over it from these coils. They're called the colloidal field coils. But the fundamental thing is that the magnetic field applies a pressure. And that pressure in my handy-dandy units is 4 times B squared. That's in magnetic field units of Tesla in atmospheres. So we typically apply magnetic fields in devices like 4 or 5 Tesla, 4 Tesla in jet, say, right? And so this is maybe 50 to 100 atmospheres of pressure. But the plasma has a pressure itself, and that's P here. And that's pushing back out against the magnetic field. And you're paying for the coil, so you would like as much plasma pressure as possible in order to make a fusion device. And so you want this figure of merit, which is called beta, which is the plasma pressure divided by the magnetic pressure. And for stability reasons, that only gets to a few percent in our devices, right? I mean, in D3D, centrally, maybe a bit over 10%, but really only a few percent in the devices. And so this is a number that physics kind of tells you for your device. So if you think about, so this is kind of conceptually what a fusion reactor would do. You have some plasma in here, confined, these are superconducting coils, which are the superconducting coils, the blue things, right? Confining a plasma, which is the red thing right there. And inside that plasma, you heat it up to a temperature, it gets to the temperature, it starts to do fusion, right? And the fusion is the tritium plus the deuterium goes to helium, which is charged, and a neutron. And that helium heats the plasma, and if you've got enough fusion going on inside there, it will sustain a fusion burn inside it. And what will happen, and the physics of this is largely decoupled from the next step. Not entirely, but if you're going to say, how am I going to build a global model of this fusion reactor? This bit of the problem is somewhat decoupled from the others. What you need to know is how much magnetic field I apply, some various parameters, and then these days we have really pretty good codes that can calculate what happens inside this plasma, and you'll get more of this in a moment. Then what happens is that produces a neutron. The neutron comes out through the wall and into what we call the blanket structure, which is here. In that blanket structure is lithium. And the neutron hits lithium And in that blanket structure, it absorbs 4/5 of the energy that came out of that fusion reaction, go into that blanket structure, and it makes tritium. Right? And if it hits lithium-6, this is actually an easier reaction to do. It makes tritium, but it consumes a neutron. If it hits lithium-7, it makes tritium and it doesn't consume the neutron. And that's nice because you have to make at least as many tritiums as you consumed. Right? And the key parameter is called the tritium breeding ratio. How many tritiums do you make for each fusion reaction that you do? Right? It's got to be above 1, otherwise you run out of tritium. Right? Because you've got to make your own tritium. But it's interesting, again, this part of the problem, right? We have codes to do this. And the fission community has developed these codes, and we know what happens to these neutrons. These neutrons strike the wall, they activate the wall, they make different nuclear elements in the wall, how much tritium is actually produced. And of course, energy is being put into this blanket in the wall, and you have to cool it with something, and that coolant takes off heat from that, and it drives a turbo generator and makes electricity. And really, your fusion reactor right here, it's just a great big steam engine, and just another way to boil water at that point. But this is calculable too, right? This bit here, if you wanted to calculate in detail, one configuration would probably take you about half a year to a year. If you wanted detailed response, we can get fast response on a matter of 24 hours to a couple of days. But if you wanted to really calculate that configuration, it's going to take you weeks with current codes. This, probably similarly, when you've put the whole structure together, right, you need to calculate all of that. And then finally, the other part of this, which is your structure, right? You've got steel, you've got things holding everything together, you've got materials in the wall, the degradation of those materials, you've got safety analysis, you've got all kinds of engineering things that you'd want to do here. That we do have codes for. The engineering industry has codes for it. It's very similar to what you would do in a fission reactor, but it's complicated and it needs real design work in order to know, do you have a good design on this? Again, weeks and weeks of work, probably months and months of work in order to get one design out of that. And this here, by the way, is you've got to extract your tritium from your lithium mixture, etc., and get it back in your plasma. And it's your whole fuel cycle system. So what I'm trying to do in this thing is to say, you could calculate all these things for the roughly 10 billion configurations that we might consider for a fusion reactor. But that wouldn't be a fast way to fusion, right? If each one took you a year, I'll be waiting an awful long time at that time. This is just for example, this is work actually from the UK, from Mark Gilbert at UK AEA. This is calculating, here's your source of neutrons in the middle coming out into the wall, and he's calculating all kinds of things like activation of the wall, etc. These are all calculable things, right? But they take a long time. Here is what happens. This is, as the neutron goes in through a piece of steel, there's a recoil of the nucleus of the steel, and it plows through the structure of the steel because it has a recoil at about 500 kilovolts. That means it's a projectile nucleus in the steel, and it destroys the structure of the steel right there, and gradually the wall will weaken. And if your wall doesn't last years, it's going to be hard to make a commercial fusion reactor. So you have to calculate all these things, right, if you're going to ascertain what's happened. And one of the problems I have, again, with the fusion companies, there's some fantastic stuff going on in the fusion companies, but they should be calculating, right? A lot of these things can be calculated, and they should be. Confining the plasma. I think I've only got about, how much do I have?
8 minutes, maybe.
8 minutes left? When we first had these magnetic configurations back in the 50s and 60s, we thought we could hold the plasma in a quiescent state. We thought, with a temperature in the middle of 250 million degrees and a temperature at the edge of a few thousand degrees, right, we could hold the plasma steady. No plasma that we've ever seen isn't turbulent. because you have a huge temperature gradient between there and there, and the thing is boiling away, basically. It's like putting anything on your hob and turning up the gas, and the hot stuff rises and the cold stuff falls, and you get turbulent saucepan, right? But what we've done is we've reduced the size of the turbulent eddies to centimeters or even millimeters across. And these measurements in General Atomics at Princeton and in Europe, have we confirmed the turbulence that's going on inside there. And very recently, we've been able to calculate that turbulence inside the device, right? And I'm going to give you a couple of little handy-dandy little pieces of physics. So the way this turbulence works is it's elongated along the magnetic field lines. But what's happening is cold plasma's going in, hot plasma's going out. You have a sort of random walk of plasma from the middle to the outside. And that random walk of plasma, the distance you travel in a random walk is the square root of the number of steps times the size of the step, right? And so there's this number, which is how many steps do you make before you get from the middle to the outside. And for a machine like the International Tokamak, that's a million steps, right? Typically from the middle to the outside. And you make that step on the turbulent timescales that's happening inside this thing. How fast is that step taking place? And that's called the eddy turnover time. And it's roughly the size of the device, this is the size of the device, the radius from there to there, divided by the velocity of a typical deuterium or tritium ion moving inside this very hot plasma, right? So the time for energy to get from the middle to the outside, the leakage time of your temperature, we call it the energy confinement time, is the number of steps times the eddy turnover rate. And this gives you a scaling on how these devices confine. Every magnetic field device basically follows this scaling, right? Most people, in the less explored devices, they haven't got there yet. But in all the explored devices that we've ever measured, this is the scaling that we find, right? And it's confirmed by lots of, it's called gyro-Bohm. But in some devices, you can minimize the turbulence by clever design of the magnetic field, clever design of the shape of the plasma, etc., and get much less turbulence. And in fact, again, General Atomics has been the masters of this. We end up with a parameter that the energy confinement time basically goes like this. This is a fudge parameter, h. H is 1 is sort of normal behavior, right? And h in General Atomics and in Princeton machines, we can get to 1.82, something like that. But it's cubed in the formula. And that's an accident of history. So h of 2 is actually 8 times better than h of 1, right? Because the energy confinement time is 8 times longer. And you want to confine your plasma, right? Now, you pay for size by the size of your device. And the European one, 9 meters, one of the reasons it's 9 meters is you have to make it big enough that it confines the plasma. Or the magnetic field, because magnetic field, you have to make a coil that confines your plasma. And if you want it to be self-heated, you want the power coming out in your fusion reactions in the alpha particles, the helium, to be balanced by this loss, which is the loss due to the random walk, the turbulent loss. And if you put all that together, and I'm running out of time, so I'm going to put it together very rapidly, you come up with a basic law for all these tokamaks, that it goes like the fudge factor cubed, the size cubed, and the magnetic field to the 4th power. And one of the more exciting private companies is Commonwealth Fusion, which spun out of MIT. They're trying to double, basically, the magnetic field strength in these devices to make a smaller device. I'm not sure that smaller will be cheaper, frankly. Lamborghinis are not cheaper than Ford trucks, but it is their approach, right? Improving the confinement is the big lever to actually get to something that's much more commercially relevant. So a number of things. For instance, the total, if you take this scaling seriously, the total power of your device goes like 1 over h cubed. So if you go from 1 to 8, you can make a smaller reactor. And smaller reactors fit into the grid much better than the great, monumental, huge things, right? The diverter heat flux, the plasma leaks heat to the edge and we sweep it off into an exhaust system, we don't want to melt the wall. If we melt the wall, then it won't survive. That's the kind of handy-dandy back of the envelope. We're doing huge calculations where we have to resolve down to fractions, a hundredth of a millimeter on scale across the magnetic field lines, the turbulent inside these devices to find configurations that confine better at this time. This technique really came into its own in the last decade, right? Because it's a 5-dimensional calculation. Because in a plasma, you can't just solve for the density and the temperature. You've got particles rushing around, so you have to solve for the distribution function, the probability density function for the particles. And that's actually a 6-dimensional function, which we average out one of the scales, and it becomes a 5-dimensional function. But these are 5-dimensional calculations, so it takes the biggest computers. And we do it because the turbulence is on very small scales. We do it in little tubes, and then we assemble the whole plasma by doing tube by tube by tube across the plasma. And once you've assembled that, you average over the turbulent timescales to get the evolution timescales. And this works. It works on D3D. It works on complicated 3-dimensional machines. And we've used it, for instance, here, this is the turbulent heat flux. This is an unoptimized condition. We've optimized the condition, and we've brought down the heat flux and made a more efficient fusion reactor by calculation. I will move on from this. That, as I said, if we were to do that and then just search the space of 10 billion configurations to make a fusion reactor, it wouldn't be a fast way to fusion. But what people are doing, and we have something called Stealth Foundry at Princeton, is replacing steps in this calculation with AI-generated surrogate models, right? And testing them both against the computation and against the data in order to get something that we can extrapolate rapidly into that space. So this is kind of where we are. This is a project at Princeton. Michael Churchill is leading it, to look at designs of 3-dimensional machines, which have some real advantages, and optimize by using these AI surrogate models. This is just an example of doing that for the turbulent simulations, for instance, that people from the University of Maryland are doing at this time. I think we've got the willingness at DOE to start to make a big push to produce basically an AI surrogate for a fusion reactor. And that's not one big AI surrogate, I think, but I'm not sure what will be optimal. It's a series of replacing steps within that calculation. And when those AI surrogates aren't accurate, knowing that they're not accurate and doing the basic principles calculation to fill out the space, etc. So it's a sort of a project. I think there's an interest right now in by 2029-ish, the end of this administration, to have really generated some designs that might become that first electricity producing reactor. Because it'll take us 4, 5, 6 years to actually go from design to something that's actually built. Some might say longer than that. Let's hope that's not true. So this is a particular moment in time that we may have a resonance with the state of art of the computation, of the world, of the administration, etc., to make AI for fusion into something that can actually deliver us electricity. Thank you very much.